Thank you very much, Mr. Chairman. I'm doing my last talk today, and this is the last day of the seminar also, so that's nice. And I will cover during this presentation 3 topics concerning application of ultrasounds. The first will concern medical applications, and that would be my first talk, and then we will move to a specific application that we are doing in our research laboratory that concern high temperature characterization of porous material and for transducer application. And the third talk will talk about the use of reverberation technique, ultrasonic reverberation technique to monitor the process and the polymerization process, for instance. And this is a work done by colleagues in the laboratory also, Osep Ashdian and Julien Bustillon. That's it. Okay. Let's talk about medical applications. I will give a brief introduction, but you know about transducer, you know about acoustics, you know about materials. So now you have all the evidence to understand what I'm talking about. We will talk about application on diagnosis, which is one of the main applications, but there are also other applications, and especially therapeutic applications that can be used. And the main difference between the two is the power level that you deliver into the body, of course, because you can understand that if you are using focus ultrasounds of high intensity, then you will create a local heat elevation like a lens in optics. So, transducer, there are, I would say, if you look at transducer in echography, maybe you may have 10 types of transducers. And on this figure, you can see conventional transducers that are used for B mode images. And eventually we will talk about 3D images later, but these transducers are, there are few transducers and compared to NDT. And I have already mentioned the reason why. This is that, in fact, the human body, or even if you are doing echography on animals, the skin is conformable. So you can put a slight pressure on your body and make a good contact with an echographic gel and transfer the ultrasounds into the body. So in a way, you can investigate the internal structure of the body with very few probes. These few probes, this will depend on the targeted applications. And for instance, you have here sectorial probes that are shown here. These sectorial probes are generally used for deep inspections in the body, like obstetric applications. You have linear probes, and this is more for high frequency applications. I would say around 15 megahertz. And these probes are used, for instance, for muscles analysis or tendon analysis and study, and so on. And you have one specific probe, which is the phased array transducer, which is used for echocardiography, where you have both focusing and deflection to image the heart. When you have to understand, and we already talked about attenuation into material, but into the body, of course, if you look at the evolution of 2 parameters, the frequencies and the attenuation, of course, higher is the frequency, higher is the attenuation, which means that the penetration depth that you can have into the body becomes lower. And higher you go in frequency, the closest surfaces, the closest structure you can image. And so you have to keep that in mind. This is that this attenuation effect in the material and in the body leads to select appropriate frequencies for images. As I say, each type of transducer will produce various types of images. So I have already discussed the internal structure of arrays, and they are all more or less the same. But of course, rectangular arrays will produce rectangular images. And to that, you have curved array that will produce sectorial images, and as well as phased array for echocardiography. It's nice to see echography was developed early after the Second World War in the 50s, and they have started to use transducer to try to make images, but the technology was not the technology, today's technology, of course. And the main development of the echography, it started in the 70s, and with the development of array transducers, and from one single element transducer to array transducers. And from array transducer, you are able to produce images. And on these slides, you can see the evolution of the image quality versus the time from 95, so 40 nearly 40 years ago, where you have a very poor resolution, to in the 90s. I don't know where is my. I can't see my. It's the 90, yeah, and to 95. This is when my second child birth, and then today. You can see the huge difference in the image quality, and this last image was produced by doing 3D image, and the image construction and reconstruction was done with the help of IA. That's it. So now it means that is really impressive. You have a quality of images that is very, very, very nice and very important. And of course, you have two trends in this area. The first for hospitals, I would say, and where you are developing big systems like this one that allows to produce 3D images, and the cost of these systems is several hundred kilo euros, which is not that much compared to, for instance, to IRM or RMN and so on. And the second trend is toward developing portable systems to spread the echography as wide with less quality, of course. But at this time, I would say that an echograph like this, the cost of which is something like 5 kilo euro, has a quality of an echograph at the beginning of 2000, where you had quite good images. And even now, you can have portable probes without any cables, where you have a Wi-Fi transmission, and you can transfer directly on your computer or on your mobile phone the images through a software. So there are two tendencies, and if you go, for instance, to a Chinese website like Alibaba, you will find such systems for maybe 1.5 kilo euro. It's really impressive. So it spread the echography to many applications and in medicines, in order to physicians to have their own echograph at home in their office to practice echography. Okay. Now, what are the classical applications of? So this is for the introduction. And what are the classical applications of echography? Of course, we all know about gynecology and obstetric. We have abdomen, the kidney, and the liver. Heart is very important for cardiac pathology, and vascular also. Thyroid imaging, muscles, tendons, and eye, etc. I think that every part of the human body is concerned by echography. There is one difficulty that is not investigated yet. This is the brain, because you have the skull, and the skull is very rigid. So you have a very strong impedance mismatch between soft tissues and the skull. And because of this strong impedance mismatch, most of the energy is reflected. Again, transmission reflection of wave is very important to understand why we cannot image through the skull. There is one exception. This is for the young baby, where you have the fontanelle, which is not completely closed. And in this case, for the young baby, you can produce images with echography of the brain. Okay, so here is some image example. These images are not definitely recent up-to-date images. Maybe they have 10 years, but at least you can see several aspects that can be treated by these images. And for instance, when you are doing this kind of examination, what you will look at after, this is about the thickness of the neck. Because the thickness of the neck can be an indicator of several pathologies for the baby. And especially 21 trisomia can be detected by measuring the thickness of the neck. So it is an indicator whether you will make what we call an amniosynthese, or I don't know the word in English, but I think it should be quite close, an amniocentesis analysis by measuring the thickness of the neck of a child. So first type of illustration that you can see. I was talking about brain imaging, and here again, you can see the formation of the fetal brain to see if it is well imaged, and particularly on this cut, for instance, which is a transverse cut of the brain. It's very important to see if the lobes that you can see here and here and here again are well defined and are symmetrical, which means that you have a clear development of the brain during the pregnancy. So this is the kind of images that you can observe also, and you have many geometrical measurements that are made and that are compared to reference measurements to see if the development of the baby is normal or not. So that's how a physician do to see if during the exam. And I don't know if you have already made an echographic exam, but he's measuring many dimensions to see if it is correct or not. There is one point that I would like to underline. This is that, in fact, we know that soft tissue are mainly made of water, but we don't know exactly the velocity in the human body, because it's a mix. You have tissues, you have water, and so on. So this is an approximate normalized distance according a velocity. It's not an absolute distance. You may have a bias in your measurement, but it is always the same bias, which makes things reliable. So another example of images is this figure. Of course, the heart images are very, very important. And of course, when you are doing this exam, and generally you do it, for instance, around 17, 20 weeks of amenorrhea, you have to make several measurements. And one of them is to see that at this time, the heart must occupy more or less a third of the thoracic cage. So if you have this info, then it means that you have a regular development. But also you can examine here clearly, and this is interesting, you have tissues. You have tissues all around that presents an echogenicity. And you can see that so they reflect waves, and the granular structure that's observed, it is what we call a speckle due to the granular structure. So you have this, and when you are in these cavities, so you have the right ventricle, the left ventricle, the right atrium, the left atrium, and here I don't know, because I'm not physician, but it could be the pulmonary vein or the aortic artery. But when you have blood circulation, you don't have signal. So it's a way to see, here in this area, you have blood or liquids. Here it should be blood. And you can see the separation. So no signal when you have blood, and when you have TC, you have a signal. What is interesting also, this is that here you can clearly see the valves that will allow the. You can see the ear beating. Of course, if you are in real time, you are producing images in real time. So normally you should be able to see the valves open and close for regular beating. So this is a classical conventional imaging. But now what physicians do very often, this is to combine this echography with Doppler measurements. And I haven't talked during my presentations about Doppler techniques, but I think that you all know Doppler techniques that allows you to measure the velocity of an object in movement according to a fixed point or even according to a moving point. And here, when you are using Doppler in echography, the moving points are the blood cells. And as it is a blood cells, you can measure their displacements. And what is very interesting with Doppler in echography, this is that, in fact, the frequency shift of the Doppler frequency in echography, even if you are using, for instance, a 4 megahertz transducer, typically is a few hundred of kilohertz. It is maybe, I would say, below 50, between 50 megahertz and maybe 500, 50 kilohertz, again, 50 hertz and 500 hertz, which means that if you send the demodulated signal due to Doppler to a loudspeaker, you will be able to hear the beat. And also, of course, with the technique, you can combine this with images. So this is what is really done very often. And you can see, for instance, here, this is the case of the liver, the vascularization of the liver. And it is very important, this technique, because combining Doppler systems with images will allow you to detect good vascularization, which is very important, of course, or vascularization problems. For instance, you may have some, and I have some other example, but especially, for instance, if you have cancer cells, it is known that these cancer cells are very well vascularized. So by using Doppler technique combined with images, you can see these cancer cells in the body. Another example that you can see is, for instance, when you are doing a renal transplant, and it is important to look at the vascularization during after the renal transplant, and you can see here all the branches that allows you to say, okay, I have a good vascularization, which means that the transplantation is okay. So combining images with Doppler system is very interesting for the physician. Of course, when you are doing heart imaging, then you can see the behavior of not only the valve behavior because you are producing image real time, but you can see also the blood flow from one ventricle to the atrium, and this to see if this blood flow is correct. So if you want to identify several pathologies, then it's clearly a powerful tool. Of course, we don't want to have that, but generally when you get this kind of exam, you have to verify all of this, okay? Another example of combining Doppler images with conventional images. This is, for instance, the case of a stent placed in the internal carotid artery. So there is a pathology that exists very often in Occidental countries. This is the fact that you are doing what we call cholesterol, and what the consequence is that you are developing lipid plaque inside the artery. And here, for instance, it can grow and grow. And what we call we call this plaque atheroma plaque, and at the end, this will obstruct completely the artery. So you can have a serious problem if it is the case. So, for instance, it means that when you walk, if the blood flow do not circulate correctly, when you walk, you will have difficulty to breathe, and so on. And this can be observed by Doppler technique, because if you know in fluid mechanics that if you have just a neck like this, at this here, and a bottleneck at one place, then we have low flow velocity before the bottleneck and high flow velocity after the neck. So you can identify a region where you have a atheroma plaques. And what is done here, this is to insert a stent at this place. So the first thing that you do very often, this is just to do surgical investigation, just to remove the atheroma plaque, and then you put a stent, which is a kind of metallic net that will allow inside the artery, that will allow the artery to be to have a regular continuous diameter. And you can combine this, of course, with Doppler analysis, and on this signal, in fact, just to mention that you can have the Doppler signal that maybe you have heard already the beat through the Doppler signal, but you have the systole and the diastole effect that appear clearly with the systole effect and the diastole effect, if I remember. That's it. So mainly this is for images, and with this, so you can see that here, for instance, we are doing rectangular images compared to sectorial images. Just a remark like this to do. Yeah, this is very interesting because I think that I have this kind of problem, and this is why I can't jog fast. But I have an injury on my tendon. This is not my echography, but here you can clearly see that the tendon, Achilles tendons, has a lesion because here in this area you have a thickness of the second of the Achilles tendon, and this causes difficulty to walk and even so you can treat by kinesiotherapy this kind of injury, but this is an illustration. So this is classical imaging that we do, but of course today we are and in medicine there are new techniques that are developed, and the first this is three-dimensional images and three-dimensional imaging. So you have seen a very nice illustration, very recent, because the first picture I've shown was made I think it was last year or maybe this year, I don't know. But there are other techniques such as harmonic imaging and contrast agent. Sorry, it missed one word, but contrast agent, yeah. And you see that these tools allows us to improve the image quality. So, for instance, this is a 3D image again that have been done. She's less recent than the previous one, but maybe it was made 5 or 6 years ago. And you can see even between this image and the first image I have shown, the great improvement of the quality of the images. And that's it. So with this, you are using a matrix transducer. The question of the matrix transducer, and I have already discussed that, this is that the number of elements that you have can be very, very high. Okay? And if you increase the number of elements, you will have problem with connections. That's it. So, how do you manage all the connection? And this is why today matrix transducer are used, but up to now they had a lower resolution than array transducer because the number of elements that you have compared to the image size, or this is like finally the number of pixels that you have on your camera is relatively low to produce these 3D images. However, with the help of image analysis and image reconstruction tools, you can now produce very, very nice images. Okay, there is another aspect to go back to conventional images, but another technique that is very often used. This is the use of contrast agent. What is a contrast agent? This contrast agents, this is simply try to put micro bubbles in the body and try to image these micro bubbles. Because this is typically air that is embedded in a small capsule. It could be a lipid protective cells, and this dissolve with time, or it could be albumin that dissolve also with time. And these air bubbles, of course, because of the strong impedance mismatch of with the soft tissue and the blood, will produce an enhanced echographic signal. And this is why, for instance, here you can see much better the vessels with the same image, with the contrast agent, the vessels, and to see the blood flow lesion than on a conventional image. because especially in the body, you can see the vascularization, and you can see the blood in this I would say these microbubbles. That's it. This microbubble into the blood, and so the blood circulation. So it is very useful also to use these contrast agents into to make images. But what people has observed, this is that in fact, when you send a wave on a bubble, the bubble will oscillate, which means that in fact, when you have a bubble that oscillates, it do generate not only its harmonic response, but it has a the second harmonic response, the third harmonic response, and so on and so on. Which means that they say, okay, it could be interesting to look at only the second harmonic due to bubbles. And so this is what people develop. This is second harmonic imaging of tissue. And they started with bubble. But in fact, the point is that this nonlinear effect due to bubble occurs also in tissues. And when you are doing second harmonic analysis, you have to remind that the second harmonic effect, so the nonlinear effect that you have during the propagation of the ultrasonic wave, depends on the power level, but we are limited on the power level, of course, because we don't want to eat the tissues in the body, but depends on the penetration depth you are. More farther you are going, higher is the harmonic response. And so, what is interesting, this is that if you consider that a patient with what we call a difficult to image, especially because in terms of linear response, for instance, you have a, I would say, it's a big patient, and you have lots of fat, for instance, on the body, and this fat will allow make that you cannot image clearly the internal structure because you have to cross this very thick thickness of fat. So by using harmonic imaging, you can avoid this effect and only look at the contribution really after the first few centimeters that you have difficulty to cross. Here, for instance, you have the same image done by conventional image and harmonic imaging, and here you have a very, very nice, a very, very nice picture. Another illustration of harmonic imaging is, for instance, kidney stones. And here again, you can see clearly the presence of the stones in the kidney with shadow here that appear. So these are new techniques, 3D imaging, contrast agent, which is now very frequent, and harmonic imaging, which is now very quite frequent also. Another aspect that you can look after, this is to develop, so that was external images that up to now I have shown, but of course you can do intravascular, intracardiac, and perioperative images. And for instance, it means that you have to develop very small transducer in order to put them into a catheter and to have images. And for instance, you can do this kind of intracardiac and intra-artery intravascular images, where you can see on this area an atheromatous plaque, for instance. So you have a circular image. And here you can imagine that you have a guide, of course, but at the beginning you had one single element transducer, and you have a rotating systems that allow to produce the images. But now developing a very small circular array transducer that allows to do the sectorial scanning, the circular scanning. There are examples of probes that have been developed for intravascular images, for instance. So this is a very nice technology. The diameter is typically 1 to 3 millimeters. Here are some comparison with ex vivo images, and we have quite a nice response with the various layers that can be observed through the artery. And of course, you can do blood flow, combine this with blood flow, and for instance, on the femoral vein, just to, for instance, avoid what we call phlebit in English. Maybe this is the same word, I don't know. But finally, in the femoral artery, or you may have some blood cluster, and this blood cluster can go up and up and up, and it may be very dangerous because you can get cardiac disease, or even vascular cerebral disease, also accident. Okay. So just going back to 3D images, you have, for instance, images of stents, and now you can see, if you go on internet, you have lots of nice images that exist, and you have a video of aortic valves, and you can see if it works correctly with 3D images, for instance. So now let's move to therapeutic applications, and the first one concerns eating. This is when the wave propagates, and this friction between particle and matter from which there is a production of heat, the first phenomenon that you can have. And if the intensity is higher, you will get cavitation and presence of microbubbles. And then if you have a very, very high intensity, you will produce shock waves. And this shock wave can destroy objects, and especially solid objects like stones, for instance. And this is one of the first applications. This is what we call lithotripsy. And here, for instance, you have a high focus ultrasounds, focus ultrasonic transducer, and it will send a wave on to destroy stones that are, when you have what we call a peritonite, and you have stone in the kidney or in the vesi, and then you can destroy these stones by using this technique. There is no other solution, because the natural, the only way you have this is to evacuate these stones through naturally. So you suffer a lot when you get this kind of disease. It is clear. So it's better to destroy the stones. So to avoid this, I just can recommend you to drink a lot of water, and it's better. That's it. Okay. Here, this is a specific application that concerns thermal applications. So for men, there is one disease that is very frequent when you become older. This is you get prostate cancer. And so this is a slowly evolving disease. It may take several years to become really dangerous, but you can, to avoid the ablation of the prostate, you can burn the cells by using high intensity focus ultrasonic transducer. And here, for instance, you have the idea is to heat up to 80 degrees locally the temperature to destroy the cancer cells. There is a photo of the equipment with first an imaging technique, and then you bring the high intensity focus ultrasounds for treatment. Okay, so these are more or less the end of my first presentation. I think that the turnover of ultrasounds, this number 2 billion is quite whole. Now it's much higher. Just want to remind that ultrasound images that are produced in echography are non-ionizing radiations. And generally, this is a low-cost exam compared to RMN. And so you can very often practice this kind of exam. Generally, it is non-invasive, but of course, you can do intravascular endocavitary measurements that produces image in real time. So that is very interesting for the physician, which means that you get directly the image. The resolution typically is from 0.1 to 3 millimeters, and it is relatively low cost, as I said, and it is multi-use, portable, and reliable. Okay. Of course, you need to be a physician to do this, but to know the anatomy and to understand all this. The perspective and their permanent evolution for, of course, having better resolution images. And they still have work on probes, on array probes, to produce richer information in terms of motion, in terms of volume, in terms of new organs. New organs like skin images, for instance, we see, which can be image or eye imaging. I haven't talked about eye imaging. There are new modalities, techniques that are mainly developed in hospital, not in a regular center when you do your echography, but like harmonic images, the characterization of tissue that allows to make some quantify the property. The elasticity, this is a new technique that is being developed, and that consists is you know that when you have a physician that do an exam, very often he puts his hand and do what we call a palpation to see if he can see some rigid structure inside. And here, in fact, he solicited the shear component of the tissue to see if it is rigid. And in elasticity, tissue elasticity, deep palpation, this is equivalent to solicitate the shear component of the tissue and try to image this shear component. And this is equivalent to do a palpation. And what is interesting, this is that the shear component has a huge difference between a good area and a bad area. So you can do what we call a palpation. And I have already talked about that, imaging of the brain. This is a nice perspective also. Okay, so here I'm going to present the work that is done by my PhD student, Dangxi Nguyen, and this is the work that we have carried out in collaboration with the CEAA and the Gremon Laboratory. And the results that I show here are mostly the results that we present during a conference in March concerning in conference in ultrasonic non-destructive testing. Just to give you first, so the title of the talk is the characterization of porous metals backing for high temperature ultrasonic transducer. So it's nice to have knowledge about transducers because you all know what is a backing now. It's nice. So here is the outline of my talk, giving an introduction and then talking about porous metals and materials. Report some characterization at room temperature and then in temperature, some transducer simulation and fabrication, and I will conclude. So we all know that there is a global warming, and one issue to avoid the global warming is to use nuclear energy, because nuclear energy is a low carbon or carbon free. And so you can use nuclear energy to produce electricity and to produce energy. And this is what is done in several countries at this time. But at this time, the technology that is used uses what we use low neutron reactors, which means that the product that you are using then will be used one time, and you can use only one time the uranium that you are using. There is an emerging new technology that is the fast neutron reactors. So the low neutron reactor, in fact, the uranium that is located by these cylindrical bars is simply immersed into water. And this will slower the neutron, and then we stop the chemical reaction, the nuclear reaction, sorry, depending the amount of signal you have. But in fact, there is a new technology that is emerging. This is fast neutron reactor that use nearly the entire amount of fissile matter. It will still remain some unfissile matter at the end, but the amount of unfissile matter will be much less than in conventional reactor. The problem is that because you use fast neutron, and this fast neutron will try to make the cascade chain for producing the nuclear reaction. The problem is with these new technologies, so it means that with these new technologies, there is also something very important. This is that the resource in terms of nuclear materials like uraniums should be something like 5,000 to 8,000 years, which means that it is no longer a problem. But the technology is very sophisticated. In particular, you have to put if you look at the core of the energy production, you have to put the uranium bars into a liquid, high temperature liquid medium, like sodium liquid. And so the question that is addressed, this is that, of course, you are in a harsh environment. How do you develop control techniques when you have materials, metallic parts, or uranium parts, and so on, that is immersed continuously without any possibility to remove them from the medium? And that is, how do you develop control techniques? And what you have to mention, this is that here, the temperature is typically, I would say, 565 degrees, I should say, if I remember. The sodium liquid, the liquid sodium is as high as this temperature. And so you have a metallic part where you may have bending, you may have cracks, and so on. So how do you control this? And so ultrasonic techniques is among the best candidates to control this technique, because you cannot imagine to do a visual inspection, and it's impossible. So you are in a very harsh environment. So a high temperature constraint, you have a radiation environment, you have a permanent immersion in sodium, and not only few hours. I mean, it is permanently immersed. And then you have corrosion and so on and so on. And so you have to control in this area, in the primary circuit, but you have many places where you have to develop control and where you have so here you have the primary, secondary heat exchanger, and then the secondary heat exchanger that will produce the electricity. And so you have to be very careful with this. And here again, you have high temperature. And so you have to put transducer nearly everywhere to be sure that you will not have a problem. Especially because what I haven't mentioned, if you are using liquid sodium, I say liquid sodium 8 oxygens. So this will create a chemical reaction that is very, very dangerous. And so we want to avoid presence of oxygen with sodium. And my colleague Nicolas in chemistry could explain the reason why, but it's definitely no. The answer is no. And this is one of the drawbacks of this technology. This is that if there is a leak of sodium, it can be very, very, very dangerous. So we want to develop the US technique for inspection of such equipment. So you know about the role of the backing, and so for instance, that has an effect on the sensitivity of a transducer and on the axial resolution of the transducer. I will not comment that much about this slide that you already know. But of course, CEA has already developed ultrasonic transducers for high temperature. And but this transducer has to answer to several constraints, and that was developed to answer to high temperature constraints. But I would say this is not an optimum design of transducer. And the transducer is made as this. So you have a front plate cover and simply a piezoelectric material that supports high temperature. Here, this is lithium niobate. And you have just a back cover. And if you look at the thickness of these plates, metallic plates in front and on the back, typically it's 1.2 millimeter on front and 2 millimeter on the back. And then you have your piezo material, lithium niobate. And here, for instance, you have a picture of high temperature ultrasonic transducer. So that's quite nice. It supports high temperature, but up to 300 degrees, 400 degrees, even higher. But there is one problem. This is a pulse echo response and the frequency spectra of such transducer. Because it is made of various layers, yeah, you have coupled resonators with the metal, front metals and rear metals. So this explains why you have many resonances. Because this is coupled, you have 3 coupled resonators. And then the consequence will be that the pulse echo response is very long. And you have, remember, it is supposed to be a 4 megahertz transducer. 4.5 megahertz transducer. Typically, the resolution we were talking about in metals or in biological tissue is something like 0.1 to 3 millimeter. Yeah, if you look at the minus 6 dB axial resolution, you have 5 centimeter, nearly 5 centimeter. And for images, looking at the minus 20 dB axial resolution, it is also something very important. It's nearly 10 millimeter, 1 centimeter, 0.5, yeah, nearly 10 centimeter. So with this, you are not able to produce image of good quality. You will do poor quality images. But At least if you want to make some telemetry, it could be maybe an interesting tool. So it's a good transducer anyway. But the constraints due to the harsh environment has limited the possible application of this transducer to images. So the idea that we address during this work, this is, are porous materials suitable to be used for high temperature backing materials? So what we could expect with such material, this is to have a high attenuation coefficient, which is one of the role of the backing. To have an acoustic impedance that you can manage by managing the porosity. You can manage the acoustic impedance of the transducer. And to have some physical and chemical property and mechanical property that should be satisfying for high temperature. In particular, these porous metals, for instance, are used for catalytic applications. So even they are known to be used up to 800 degrees. And then the point is that they also have to get a thermal coefficient expansion that is compatible with the lithium niobate material, which is the active material used for transduction, the piezo material used for transduction. So this is what we could expect. This is what we need for this material. And in addition, porous material, they have some electrical properties. They are conductive material, and they present the possibility to have a brazing capability, which means that we can think about transducer assembly. So many expected quality. So we in this work we have we get some samples and we have them characterize them. So here, this is the material on which we have worked. This is porous stainless steel. Porous stainless steel, you have an electron micrograph here, just to show you here the diameter, typically, depending on the porosity. Here you have 52% of porosity. You have pores that are typically, I would say, 100 micrometers. But this is open porosity. And here you have this sample with 25% of porosity with smaller pores. And here you have the characteristics that have been measured from the various samples that we have. So we have, for our experiment, samples ranging from 25% of porosity to 52% of porosity. So the first thing that we did, this is to make insertion characterization at room temperature. At room temperature, we have used a classical experimental setup. We send a pulse using these techniques. And by measuring the time delay between the reference signal and the transmitted signal when we have insert the porous metal, then we deduce the celerity into the material. And because we know the celerity, we can calculate the transmission reflection coefficient at the interfaces, and then we can deduce the attenuation into the material, which is a specific criteria that we need to play the role of backing. So here we report the measurement of these properties for the various signal that we have. For each measurement, we have something like 10 samples characterized that allows us to determine both a precision measurement on the porosity and on the velocity measurements. What you can see here, this is that the density varies linearly with the porosity content and ranges from 4,500 to less than a little bit more than 2,000 for 50% or 52% of porosity. Of course, because you increase the porosity, and this is air porosity, you decrease the acoustic impedance. And surprisingly, in this range, the porosity still remain the acoustic impedance still remain linear here. So you can decrease the porosity and you can control the acoustic impedance, which is very interesting. If you can control the acoustic impedance of the backing, it means that you will be able to control the bandwidth of the backing, the bandwidth of the transducer and the sensitivity. So that is very important. And another parameter, which is very important, this is look at the attenuation. When you increase the porosity, then you have a huge increase of the attenuation. And even with 55%, 52%, you have an attenuation of 4 dB per millimeter. This criteria is very important because if you, in terms of development and technology, you will use a finite thickness backing material, and you want to avoid round-trip echoes. So that's so what I say, a backing of 20 millimeters leads to an attenuation of 40 dB at 1 megahertz, which is largely sufficient for developing imaging systems. So this is the result we had for low frequency, low temperature measurements. Of course, we move to high temperature, and to do so, we have used a high temperature transducer. This transducer has the following characteristics. It has a center frequency of 2.5 megahertz, a diameter of 10 millimeters steel. In fact, this transducer is mounted on a delay line, and it can range from ambient to 500 degrees. And the point is that you cannot use this transducer more than 2 hours at high temperature. And we had very strong problem with this transducer because the contact breaks here, and here this is a rigid 50 ohm cable, and you have a break here, and we lost the signal at the end of the measurements. So we have to send it back to the manufacturer to repair it. And here you have the echoes, for instance, of the transducers. We have developed an equipment, so you can see here, with for contact measurements. So you have the sample, and we have developed a sample holder where you put the transducer in contact, and you use a specific coupling that supports high temperature, and it is in contact, and we measure the round-trip echo and as a function of the temperature. So we have a pulsar receiver that is connected to an oscilloscope, and of course, it is placed into a furnace, and in parallel to ultrasonic measurement, we measure the temperature. These measurements were done at the CEA. And here you have a photo of the equipment with the sample here, the transducers. And here I think that it is, no, this is we can't see the thermocouple. It's not there. Okay. Mm-hmm. Here are the typical signals that we have and that we need to interpret. So the first signal is a round-trip echo in the delay line. And then you have the round-trip echo in the sample. And so you can focus on this and look as a function of the temperature, how it varies as a function of time. That's it. And here, this is a measurement, for instance, that we have done on the sample at 35% of porosity at 2 megahertz. Okay. Here we had one problem. This is that it's not easy to measure the attenuation into the material because we are using contact transducer. But so what we can say, this is we are able to measure variation of attenuation because everything remains the same when the temperature varies. So on this figure, we have the relative celerity variation and the relative the attenuation variation that we can observe versus the temperature. First, we could test two samples. One, in fact, three samples. One with zero porosity, plain metal. One with 25% porosity, and one with 35% porosity. And what we can see, the first, if we look at the relative celerity variation into the samples, then we can observe a linear dependence, and higher is the porosity, but this has to be confirmed by other measurement at this time because we have only two porosity. Higher is the celerity variation. And typically, here, when you reach 400 degrees, you have between a little bit more than 6% celerity variation into your metal. So for this sample, for instance, at 25%, just to remind that the celerity, when you have a 25% porosity material, this is something like 440 meters per second. So you have 6% variation, which is not that much. Now, what is observed here, this is that if we look at the attenuation variation, so of course you can see maybe a general tendency for the plain metal to an increase of the attenuation with the temperature. But if you look at the porosity, the porous metals, I'm not sure that we can really conclude if we had an increase of the attenuation, because I think that the accuracy of our measurement technique do not allow to clearly conclude to an increase. And at least if you look at the values of the attenuation variation, it is 0.1 dB, which is very low, which means that in fact, the attenuation into the porous metal doesn't depend on the temperature. So we can simulate transducer at room temperature and with attenuation that we have measured at room temperature to make these transducers. That is the conclusion that we can have. So this is what we have done. We have done using the KLM model. So just an equation here. But I don't go into detail about the KLM model, but this allows us to predict the electroacoustic response. It is based on a matrix transfer multiplications, where each component of the transducer and even electrical or mechanical is characterized by a matrix transfer. And the total matrix transfer will allow us to determine the transfer function in emission, the reception transfer function, the pulse echo transfer function, the 50 ohm loop sensitivity, and so on. Let us show some simulations on the reference transducer. So the reference transducer in lithium niobate base cut. The crystal has a diameter of 40 millimeters. The coupling coefficient is relatively low in this crystal. This is 0.17%. Remember that in ceramics it's 0.5. And the characteristics are given here. And on this figure, you can see the simulated and experimental pulse echo response. Even if it doesn't fit exactly the response, you can see that general tendency, we will predict the temporal response of the signal. And in particular, this can be seen on the spectra, on the spectrum, or when you look at the two spectra, the experimental one and the theoretical one, where you have the multiple resonance that are well predicted by the KLM model. And of course, you always have a difference between theory and the experiment. And here you have additional resonances that can be due to the brazing that create an additional layer, for instance, between the rear plot and the lithium niobate. We have done a study on the influence of the backing acoustic impedance on the electroacoustic response by varying the impedance from 10 to 30 megaRLs. And if we do vary this value, we can see that for high impedance, of course, you shortened the response. So these are normalized response. But of course, if you look at the transfer function, which is also an indication of the sensitivity, you smooth all the resonances and you lower the sensitivity, of course. And so you have a shorter response, typically. And when you lower the impedance, you maintain the resonances that exist into the transducer. And of course, you have these resonance peaks that appear. But remember that if you look at the time base here, the time base is from 0 to 8 microseconds. Go back to the time base of this. It goes from 0 to 100 microseconds. So in any case, the transducer response is much shorter than the reference transducer. Even if you can see what you can imagine, long response systems. It has, of course, an impedance on an influence on the sensitivity, so you can do this study also. As you increase the impedance, you lower the sensitivity because more energy is capped in the rear face of the material. And of course, the consequence is an enhancement of the axial resolution, but these results have been already discussed during my previous talk, and it is quite obvious that we get these results. Here is, for instance, with the two material, we have made a simulation of the transducer with 25% porosity and 35% porosity. The sensitivity is, predicted sensitivity is minus 54 dB, and an axial resolution of 1 millimeter at minus 6 dB. And on one case, and for the second case, so the 35% porosity, the acoustical impedance is slightly lower, so you have a longer response. Nevertheless, the minus 6 dB resolution still remain around 1 millimeter, but you have increased the minus 20 dB axial resolution, so and of 1 millimeter. But it is still much better than that of the reference transducer. Here is a simulation that shows the influence of the backing thickness, for instance. And if you do this calculation it was done for the 35% porosity material, where you have, you can see the round trip echo in the backing. And then when you have a 30 millimeter, this round trip echo becomes slower, and then for 40 millimeter, it's totally vanished, and the attenuation is something like 40 dB. We have done this simulation, and this was what we have presented at the conference. But recently, we have made a transducer, a very simple transducer made of lithium niobate single crystals and electrodes that were made with silver paste, and it was glued with this silver paste on 25% porosity backing. So you have here a picture of the transducer with a holding system, and here you can see the crystals, and here you have the backing that is here, and we have here you have contacts here, and we have made measurement in our laboratory. So you can see the equipment with a pulse, a function generator that will deliver a pulse, and then send to the transducer, and then you measure the round trip into water, and then you observe the echoes. This is a basic measurement. There is a direct signal that you have, so from which you can deduce several characteristics. The axial resolution is 3 millimeters, and it is measured directly on the envelope of the signal. But here what you can observe, this is that you have here a second echo that appears. And in fact, if you do the calculation of this time delay, that corresponds to a round trip with no backing. So it means that it's not highly, we have only 1 centimeter thick materials. It is clear that a thicker backing material would be nice. You can look at the frequency spectrum and the sensitivity. Here, the sensitivity is close to minus 25 dB. And the bandwidth of the transducer at minus 6 dB is 9%. And here, you can see oscillations on the spectrums. And these oscillations are due to multiple reflections inside the backing material that creates resonances into the systems. That's it. And these results are very recent. They have been obtained this summer. So in conclusion of this work, we have there is a clear need of a high temperature ultrasonic transducer to image defects and to improve the axial resolution. Porous materials can support high temperature. They are good candidates. They are compatible with high temperature. They are conducting materials. There is one thing I haven't mentioned. This is that here on the rear face of the transducer, the backing can be used as a contact electrode, which simplify the technology, of course. And if on the front face you have a protective metallic layer, and in between an insulating layer, then you won. You have your transducer. And so they are compatible with high temperature. They are conducting material that allow direct electric contact on the rear face. We have made some characterization of porous material between 25 and 52 degrees at room temperature. Due to the celerity change ranges from 4,500 meter per second to 2,200 meter per second at 52%. The attenuation ranges from 0.5 to 5 dB. And we have made some characterization at high temperature on 2 samples. We have a decrease of the celerity of something about 5% on a temperature range of close to 400 degrees. No attenuation was observed. We have simulated and fabricated a high temperature transducer, and we have characterized this transducer at room temperature. And we do observe a strong improvement of the axial resolution compared to conventional transducer. However, still work remains, because one thing I haven't mentioned yet, this is that it does not compare very well with simulations. So we have to find the issue why it does not compare very well to simulations. And so that's future work, and to conduct tests on temperature and do this comparison between theory and experiment, and test other cuts for lithium niobate materials, because this cut has a low cut. It's a low coupling coefficient. That's it for this presentation. Okay. And now I have 10 minutes. So there are 2 options, Mr. Chairman, Tetsuya. Either I stop there and then we open the discussion, or I move to my last talk. What do you prefer? The last one? Yeah? Okay. Okay, it is shorter. I have 15 transparencies, and I will just present some major results on this technique. This technique is quite interesting because it's a quite recent technique that is used in NDT, and this is the idea of using the reverberation that exists in materials to deduce information about the material property and material attenuation and material evolution. So the framework, this is in fact doing monitoring process of physico-chemical transformations in various industrial sectors. So it could be food industry, but it could be also cosmetic industry, or it could be, for instance, hydrogen and technologies with a reservoir tank where you want to monitor the polymerization during, for instance, the water filling. The hydrogen filling, or during the fabrication of liners in hydrogen tanks. And for instance, there is one point that is very important. This is that in these tanks, here you have a metallic part that is in contact with the liner, because hydrogen will be taken out and the inlet through this metallic part. And if you have a degradation of the bonding between the metallic part and the liner, then you may have leak of hydrogen, which is not desirable. So non-destructive technique is, of course, a powerful tool. We know that. And we can have some acoustic parameters, such as the wave velocity, the acoustic impedance, the attenuation, but also the reverberation times in such structure that are linked to defect, to cracks, to transition, and so on. So what is the main difference of between conventional NDT techniques and reverberation techniques? The idea of NDT techniques, and I have discussed of that, this is that, okay, what we are looking for, this is the direct echo. And we only look at this after that. But in fact, in practical, if you look at what we call the coda of the signal, after the first round trip echo, you have the first round trip echo, you have multiple reflections that occurs in the samples. And these multiple reflections will decrease with time, but it is clear that you have a global information on the material properties if you try to analyze the signal due to these multiple reflections. And typically, this is the problem that we have when we are doing room acoustics. When you are doing room acoustic, you will look at the reverberation time into your room, and then you will deduce if it is a long reverberation time or a short reverberation time. And for instance, if you have the presence of a defect into the metal, then you will have another coda, and the difference in codas will tell you, okay, there is a problem in my material or not. So we are particularly interested in exploiting the long duration signal. So just to what we were looking for, this is if we have a source here, then you will have the persistence of the sound in the hole after the source is stopped. And what we will look after, this is this decrease of the persistence of sound. And we can use a very well-known formula used in room acoustic. This is the Sabine formula that gave us the attenuation in a room by, depending on the volume of the room, the surfaces, and a parameter alpha that has to be defined. So this allows the estimation of sound absorption in concrete walls or in characterization and absorption of coating, for instance. So now we have used various techniques that already exist, such as time reversal techniques, CODA interferometry, field correlation, to develop and to use deterministic relationship between two measuring points. But this method is to have an ensemble averaging of reverberated signal to extract additional information. Develop simple data processing, having few sensors. And one of the major advantages of this technique, this is that no time synchronization is required. So first of all, the Sabin formula has been adapted. And so this is not the same type of room. I don't know which one do you prefer, but this one is a very nice concert hall. And this is our concert hall, for instance, on which you will put some polymers, for instance. And then the walls will be the interface between a sol gel, for instance, techniques. So here is the typical experiment that we can have. So few sensors, an aluminum block on which you put your sol gels, and then you record the signal through an oscilloscope and transfer for treatment on MATLAB. So you have to estimate the attenuation and the Sabin absorption time, and you can look to do so by doing the Schroeder integral. And then you have the magnitude of the amplitude versus the time that you can represent. So the scale time is typically milliseconds. Why I remember in ultrasonics, the scale time is microseconds or a few tenths of microseconds. And so you can measure the slope and the time, determine several parameters. Just to illustrate this, and I will just be quite fast because the time is running. Here you have simply the transducer in contact with the aluminum plate and with one reverberation time. And then you have deposited a solution of, here if I remember, it is Salol solution on it. And so you can see the reverberation changes. And then a solution with high absorption, here again, the reverberation time changes again. So you can monitor global change with this technique. So, and just to illustrate the various point where you are. And I think that's, I will finish just by presenting, for instance, the transversion estimated reverberation time as a function of a temperature during the transition. This is Salol. Salol is liquid over 36 degrees and solid below 30 degrees. So you can see the transition here. That's very interesting. And I just finished here, just to say it's just 12 and I have taken all my time and not that more. Okay. Well, thank you very much all for your listening to me. And I just want to finish to have a kind of general conclusion about this seminar. When you're doing ultrasounds, in fact, I think that it is quite fascinating because this is a very transverse area, research area. Because if you want to understand ultrasounds and interaction of waves with ultrasounds, you have to know about materials, about waves, but you have to know about transducer and mean about electronics, and you have to know about acoustics. You have to know also about piezoelectrics, and which means that you have many areas that you need to know to understand ultrasonics and to be able to interpret ultrasonic signals. And I think that it is quite fascinating to have this kind of transverse analysis. Thank you very much for your attention.